for today, of course, right, we're going to be running, of course, an experiment. And the goal here will be to determine, so here's our goal, to determine, of course, the chemical formula of a given hydrate, right? So our goal is to determine the chemical formula, of course, of a given hydrate. And so the first step is that you guys are probably by now all familiar with the chemical formulas, but what exactly, right, is a hydrate? So hydrates, please note, these are typically what? These are just ionic compounds that have, of course, what we call bound water molecules. And there are several, right, not several, there's thousands, of course, of known hydrates. So for example, if you purchase, of course, let's say barium, of course, chloride, for example, barium chloride, of course, is actually comes as a hydrate, right? And inside, with this, of course, ionic compound, there's actually, for every 1 mole, of course, of barium chloride, believe it or not, there's, of course, 2 moles, of course, right, of H2O. Now, when we go to write the chemical formula for these, of course, hydrates, please recognize the fact that we use that dot, right, to determine, right, to at least to emphasize that, of course, it's the bound water molecules to that ionic substance. Now, in terms of nomenclature, right, if there is 1 water molecule bound to my or ionic compound, it's going to be the monohydrate. If there is 2, the dihydrate, 3, the trihydrate, 4, of course, 5, of course, the pentahydrate, right, and so forth. And so please note, in today's lab, the goal will be for you to determine what? That yes, I do know, of course, that I have an ionic compound, of course, of copper 2 sulfate. But the challenge, of course, is, right, how many, of course, right, water molecules do we have, of course, bound to this, of course, for each mole of copper sulfate. Okay, and so when H2O, of course, is bound, of course, to our ionic substance, it's referred to, of course, as what? As a hydrate. And so in today's experiment, you're starting off, of course, right, with a hydrate, of course, of copper 2 sulfate. And so please note, copper 2 sulfate with these bound water molecules, right, is a blue crystalline solid. So it's blue in color. For some hydrates, right, on heating, and so in chemistry, we tend to use that, of course, symbol delta, just to represent heat. On heating, what do you think is going to happen? Well, of course, if there's bound water molecules, right, the water usually what? Evaporates. So the water molecule will evaporate. And what you're left with, what's going to be remaining, of course, in this container, right, is just, of course, what? Copper 2 sulfate. It is still, of course, a solid. The water is going to evaporate, right? So H2O, of course, is going to be recorded, of course, as our gas. Now, as always, our equations must be balanced, right? So if there is X, right, moles of water that's bound, of course, to that crystalline solid, you should realize, of course, that we're also going to do what? We're going to produce X moles, of course, of water at the end. And so, believe it or not, you're going to be able to use this information, right, to determine the chemical formula. And now let's see how. Well, you will know the mass of your copper sulfate X H2O molecules at the end. On heating, what's going to happen? Water is going to evaporate. And so at the end of this experiment, please note, you will form what? Copper 2 sulfate, right? And that is said to be, when it's void, of course, of water, when water, of course, is eliminated, then our salt is said to be the anhydrous salt. So you're going to record, right, the mass, of course, of your anhydrous salt. You're also going to record by differences now, right? Do you agree if you know the mass of the hydrate? If you know the mass of your anhydrous salt, because, of course, matter, right, mass is conserved. Do you guys agree? Then, of course, you should be able to determine what? The mass of H2O. From the mass of water and the moles of water, then you should, hopefully, following through with our calculations, be able to report exactly, of course, the correct formula. Please note, several color changes will probably occur, of course, in this experiment. Most hydrates are usually colored, not all, but most are. And on heating, I assure you that you will observe, of course, a color change. So please note that as we proceed, of course, in this experiment. Alrighty, so for this experiment, right, we will need, of course, a crucible, along, of course, with the lid. In addition to that, of course, the crucible, of course, is sitting directly on what is called, or if there's a clay triangle. Here again, of course, is our ring, our stand, and of course, our Bunsen burner. At the side here, of course, I have my tongs, along, of course, with my wire gauze. So, of course, once my object is, of course, is hot, I can then transfer it. Please note, right, to cool before weighing. We have these wonderful igniters as well that we will use, right, to actually, of course, light our Bunsen burner. And so, at the beginning, I need for you to note your copper 2 sulfate X H2O, right, is of course what it's a blue solid. And so prior to the start of this experiment, what I did, of course, I actually went ahead and I recorded, of course, the mass of the crucible, of course, and lid after heating. So I heated, of course, the crucible and lid for about 10 minutes. I allowed it to cool, and then I recorded the mass of that crucible and lid. Alright, so as I said to you earlier, right, the crucible and the lid was heated, of course, initially to remove, of course, any moisture and any, of course, impurities. It was allowed to cool for 10 minutes, and so the mass, of course, of the empty crucible and lid was actually 43.314 grams. To, of course, the crucible, please note, we're going to be adding, right, our, of course, hydrate. And then I'm going to record the mass of the crucible, the lid, right, and our hydrate. So in our next step, we're going to begin, of course, the heating process. Keeping in mind, of course, that the lid is going to be slightly ajar in the beginning for several reasons. We want to make sure, of course, that the water is slowly evaporating, right? But of course, while the lid is open in order for that, of course, to occur. Please do not, if you do set this up on your own, open that lid completely. Why? Because of course, right, there might be splattering, and then you might of course lose some, of course, of your starter material. Likewise, we're going to be heating this, of course, gently, and again to avoid any splattering. So I'm now going to turn the gas on, and using my igniter, I'm going to actually, of course, right, light my flame. A few things I need for you to note, and I might not be able to clearly see it with this Bunsen burner, but there's actually, of course, 2 cones. Even though I can't not see this clearly, and you might not be able to see clearly as well. So there are 2 cones. There's, of course, an inner cone, right, and an outer cone. When the experiment calls for us to heat this, of course, vigorously, you want to make sure, right, that you look at that tip of that inner cone, and the tip of that inner cone should be sitting, of course, right, at the bottom of your crucible. And that's when, of course, we're heating strongly. So the hottest part, of course, of this, of course, flame will be the tip of that inner cone. But initially, please recognize, of course, that I'm just going to start off heating this gently to avoid any splattering. And so if you recall, right, if you're following through with the experiment, we're going to heat this gently for about 5 minutes before, of course, heating strongly. And now this seems a bit too low for me, so I'm going to take a few minutes and just elevate my ring. Beautiful. So we're going to allow that to go for about 5 minutes, and then of course we'll heat strongly. Please note, this experiment also calls for us to allow it to heat strongly for about 10 minutes, allow it to cool, right, and then reheat. So the goal is to make sure at the end that we're heating to constant mass. Okay, so after the crucible and lid was allowed to cool, I recorded the mass of the crucible and lid, and that's going to be, of course, 44.0212 grams. So that's, of course, the final mass, right, of the crucible lid with, of course, our anhydrous, of course, compound. And just to make sure you can observe, right, that we went, of course, from what? From that blue crystalline solid of copper 2 sulfate .x water, the hydrate, to, of course, just, of course, it has a tint, of course, of blue, but it's really, of course, a white solid copper 2 sulfate. And, of course, it's void of water, so therefore this is referred to as the anhydrous salt.